what if the vacuum of space isn't empty? What if it's not a void at all, but a real physical substance, a cosmic medium with properties like stiffness and density? Well, that's the radical new idea we're diving into today. It's a theory that tries to solve some of the absolute biggest mysteries in physics by changing our most basic assumption about what empty space really is.
But to really get why this idea is so revolutionary, we first need to look at the massive problems it's trying to solve. And trust me, these are the kinds of questions that keep cosmologists staring at the ceiling all night.
First up, we've got dark energy. We look out at the universe and we see that it's not just expanding. It's expanding faster and faster. Something is pushing everything apart with more and more force, but we have no idea what this mysterious energy is or where it's coming from. It's a huge question mark. And then there's gravity. It's one of the four fundamental forces, but it is just ridiculously weak compared to the others. I mean, think about it. You can overcome the entire gravitational pull of planet Earth with your leg muscles just by jumping. So why is gravity the odd one out? Why is it so feeble?
And maybe the biggest question of all, what even is mass? We know things have mass, but what does that mean? What is it that gives an object substance and inertia? This question cuts right to the heart of what reality is actually made of.
So you've got these huge, seemingly separate problems. How could a single theory possibly hope to answer all of them? Well, the answer is an incredibly elegant, if strange, idea. The vacuum isn't nothing. It's a dynamic, physical field. And that is the core concept of what's called dynamic vacuum field theory.
So what does that actually mean? DVFT asks you to imagine the fabric of space itself as a substance, something that can be bent and stretched and compressed, just like a physical object you could hold in your hand. The idea is that everything we see, from quantum weirdness to gravity, might just be the physical mechanics of this underlying medium. Okay, so at the very heart of this theory, there are two fundamental properties of this vacuum medium. Two completely different kinds of stiffness that, if the theory is right, could govern just about everything in the entire universe.
So let's break that down. This theory splits our understanding of the vacuum into two key properties. On one side, you have phase stiffness. This is what creates the rules for the very small, the quantum world, which you can think of as ripples in the vacuum. And on the other side, there's amplitude stiffness. This dictates the rules for the very large, the cosmic world of gravity and mass, which we can think of as dense in the vacuum.
All right, let's start with the quantum side of things. How does this phase stiffness, this resistance to ripples, give rise to the famously strange rules of quantum mechanics? The best way to picture it is to imagine the vacuum as the surface of a perfectly still, glassy lake. Phase stiffness is just the property of that water that resists being disturbed. It wants to stay smooth. And this resistance to ripples is what enforces the stability of all the quantum rules, allowing for things like entanglement and superposition to exist across huge distances.
And the scale of this stability is, well, it's just absolutely mind-boggling. The theory actually calculates the vacuum's coherence length to be about 10 to the 27th power meters. That means the quantum rulebook is consistent across a distance that's roughly the size of the entire observable universe. This universal consistency also helps explain a major puzzle called the horizon problem, why parts of the universe that are too far apart to have ever communicated look so similar.
So here's the real kicker. This one single mechanical property, the vacuum's resistance to ripples, it doesn't just explain one thing. It potentially connects a whole laundry list of seemingly unrelated phenomena. We're talking everything from why quantum mechanics works, to the value of fundamental constants, to tiny anomalies in particle physics, and even some of the surprising things the James Webb Telescope is seeing about how fast the first galaxies form.
Okay, so that's how ripples in the vacuum could govern the quantum world. But what about the dense? Let's look at how the vacuum's other property, its other stiffness, could be the source of gravity itself.
This is the vacuum's other key property, amplitude stiffness. For this, think of the vacuum like a giant block of cosmic jello or a huge rubber sheet. It resists being squished or dented. And in this theory, that's literally all that mass is. It's just a localized spot where the vacuum has been dented or compressed.
And this leads to a really profound shift in perspective. It means gravity is no longer a fundamental force that pulls things together. Instead, a massive object like our sun creates a dense dent in the vacuum around it. A planet isn't being pulled by the sun, it's simply rolling down the slope of that dent. Gravity becomes an emergent effect of simple mechanics.
And here's where it gets really compelling.
From this one property, this amplitude stiffness, the theory calculates the amount of energy locked into every cubic meter of the vacuum. And that number? It just so happens to align perfectly with the observed energy density of dark energy. All of a sudden, dark energy isn't a mystery. It's just the potential energy being stored in the stiff vacuum itself.
This idea also offers a really neat solution to the whole dark matter problem. You know, the mystery of why stars on the edges of galaxies spin way too fast? Well, this theory suggests that the vacuum's stiffness isn't constant everywhere. In dense places, like our solar system, the vacuum is very stiff. But way out in the empty regions on a galaxy's edge, the vacuum becomes softer. And this softer vacuum is easier to dent, which amplifies gravity's effect right where you need it to, explaining that fast star rotation without needing any invisible matter.
So let's pull all these threads together now and look at what is maybe the most profound implication of this whole theory. What happens when you start to see the universe not as a collection of arbitrary rules, but as one single mechanical system?
Well, the biggest constants in physics, those numbers that basically run our universe, they might not be fundamental at all. For 100 years, we've just assumed they were baked into reality at the Big Bang for no particular reason. But this theory suggests they aren't random numbers. They are simply emergent properties that arise from the physical mechanics of the vacuum.
This table really shows the shift in thinking. Take the speed of light, c. In the standard view, it's just this universal speed limit. In this theory, it's basically the speed of sound through the vacuum medium. It's the maximum speed a ripple can travel. Or look at Newton's constant, g. It stops being a measure of gravity's inherent strength and instead becomes a consequence of how stiff the vacuum is. The reason gravity seems so weak is just because the vacuum is incredibly hard to dent.
And that's really the crucial point here. What makes this theory so compelling to so many physicists is that it takes a dozen or so seemingly random fine-tuned numbers and replaces them with just two simple mechanical properties of space itself: its resistance to ripples and its resistance to dents. It provides a physical cause for all the effects we see around us.
Which leaves us with a final, fascinating question to chew on. If this theory holds up, is everything we know, from the tiniest quantum particle to the largest galaxy cluster, is it all just the churning and vibrating mechanics of a vast, invisible cosmic ocean that we call the vacuum? Thanks for joining me on this one.